So good morning, good afternoon, everyone. My name is Daniel Lancilotti Kimura. I'm a CNRS researcher at the Center of Nanoscience and Nanotechnology, and it is my great pleasure to chair this second half of the morning session of the Topological Matter Conference. In this last presentation, we have the pleasure to welcome Ingrid Mertig from Martin Luther University Halle-Wittenberg. She's gonna talk about transversal transport coefficient and topological properties. Ingrid, the panel is all yours. Thank you very much for accepting giving this presentation.
Well, thank you very much for the introduction and welcome everybody to my talk. And I would like to talk about topological properties and Hall effects, and I would like to give you, wait a moment. Oh, I cannot move, sorry. I cannot,
Part of the slide, there are arrows.
Oh, yeah, okay. I use these cursors. Okay, thank you. My cursors don't work. So, okay. After a short introduction, I will talk about the topological Hall effect, and I will show you that the topological Hall effect and the anomalous Hall effect and even the quantum Hall effect are very similar, and I show you why. And if I would have time, I would talk about the magnetic spin Hall effect. So now, transversal transport coefficients. The Hall trio started with the discovery of the Hall effect already long ago, which is the separation of electrons or charges by the influence of a magnetic field. And as a consequence, we observe a Hall bias. A short period later, Hall himself discovered also the anomalous Hall effect, where he investigated, instead of a regular metal, he investigated ferromagnet. And the ferromagnet has a magnetization, and for this, the number of electrons with spin up and spin down is different, and you also observe by this separation a Hall bias. And then there was the idea that this separation by spin should also occur in non-magnetic materials, which leads to the proposal of the spin Hall effect. And the anomalous Hall effect and the spin Hall effect are similar in the sense that the origin of both is spin-orbit interaction. And spin-orbit interaction can be described in a semi-classical manner by the Berry curvature. Now, let me consider the semi-classical equations of motion for an electron in external fields. Everybody knows that k dot is proportional to the electric field and to a Lorentz force term that is caused by a magnetic field. And a similar equation of motion is for r dot, where we have Ehrenfest. R dot is given by the velocity due to Ehrenfest, and only in the 90s, Jean New discovered a new term, which is proportional to k dot cross omega, and k dot is, of course, change of momentum, and omega is the Berry curvature. The two terms, the Lorentz force term and the Berry curvature term, are similar. They look like forces. The Lorentz force term in real space and the Berry curvature term in k space. Now, the consequence of this new term are non-diagonal, either the consequence of the Lorentz force term and the new term are non-diagonal elements in your response tensors. And I have just Ohm's law here, and these are the non-diagonal elements of the conductivity tensor. Now, this Hall effect, these different Hall effects have different sources, but I would like to concentrate to this so-called intrinsic source of the Hall effect, which is related to the Berry curvature, and which gives, we can find a very simple formula for the non-diagonal element of the conductivity tensor. And this is the anomalous Hall conductivity, which is here given by an integral over the Fermi sea, all the occupied states, and then weighted with the Berry curvature. And here we have the quantum of conductance, E square over H bar. And so all states contribute to the conductivity. And the Berry curvature here can be calculated by this formula. I don't want to go into detail, but the Berry curvature from this formula you see, this is the sum over all bands. But you observe a Berry curvature for a certain band by the influence of all other bands. This is what it means, this special sum. And these are special matrix elements that you have to calculate with the velocity operator. Now, if we consider topological insulators, the situation is a little different from what I discussed until now. I discussed systems where the Fermi level is within the occupied states or is within a band. Now, in the case of topological insulators or of insulators in general, the Fermi level is within a gap. And but if we have a topological insulator, the edge states are bridging the gap, and we get again conductance or conductivity. And this leads now to, we do the same calculation for the conductivity as before. I use the same formula as before, as I explained to you before. The only difference is that this formula gives now an integer number of the conductance quantum. And this integral that gives you an integer number is a topological invariant, and this is the Chern number. And so in this respect, transport is now quantized, since the Chern number is related to the number of edge channels that we have, and each edge channel contributes or carries to the current this E square over H bar. And as a consequence, we observe the quantum Hall trio. Before, I just discussed the regular Hall effects in regular materials, but for the systems that I discussed now, the topological insulators, we would observe the quantum Hall effect, would observe the quantum Hall trio. And this is the quantum Hall effect, where we have a pair of edge states in an external magnetic field, and the two edge states with opposite spin propagate in the same direction. And they would contribute to the conductivity 2E square over H. Then we would have the quantum spin Hall effect. And we wouldn't have an external magnetic field, but we would have a spin-orbit interaction or Berry curvature as discussed before. And we would have a pair of edge states in the gap, and the two electrons would, would propagate in opposite direction. As you see here, the little arrows of the propagation direction are different. So we would not have a current. The same way we didn't have a bias for the spin Hall effect for the trivial Hall effects. We would not have a current here, but we would have a spin current. And of course, then there is the analog to the quantum anomalous Hall effect, where we have, instead of the external magnetic field, the magnetization. And we would have exchange splitting, and we would not have a pair of edge states, but just one with a certain spin direction. So this would be the quantum version of the anomalous Hall effect. Now, let me consider the topological Hall effect in comparison to the Hall effects that I discussed before. So the topological Hall effect, let me go back again. I would like to mention my collaborators. This work was done together with Børge Göbel and Alexander Moog and with Jürgen Henk. So we did some work in this respect, and this would be the way of measuring the effect that we want to discuss. It's a regular Hall measurement, but we would have a system with a chiral spin texture at the interface, and we would have a two-dimensional electron gas next to the chiral spin texture. And as a consequence, we would observe a charge current and a spin current in the transversal direction to the regular current. And we would have a gate to observe some variation in energy. So now let me go to this chiral spin texture that we would like to have at the interface. And these are, for example, skyrmions. This is an experimental observation by the group of Torkura of a skyrmion texture. And this would now be our skyrmion lattice. And we calculated for this skyrmion lattice. We calculated the electronic structure of free electrons in such a spin texture, in such a skyrmion lattice. The unit cell consists of many atoms, and these atoms in a unit cell form a skyrmion. And this is described by this, these skyrmions form this spin texture. And the electrons, the free electrons moving in the spin texture are coupled to these magnetic moments by this Hund's rule coupling term. And as a result, we observe band structure. And since we have, we start to tune the band structure by the size of the magnetic moments. And we start with zero magnetic moment, m over t, it's the hopping integral, is zero. And the result is a band structure. Since we have so many atoms in the unit cell, more than 100 atoms, the bands are highly degenerate. If we now switch on gradually the size of the magnetic moments, so the degenerate bands are split, and we finally end up in the so-called adiabatic limit. So all the electron spins, when the electron is propagating in the spin texture, the electron spin aligns always fully to the underlying texture. And in this respect, we observe a polarized electronic structure with two blocks. Spin parallel to the spin texture is the lower energy, and spin anti-parallel would give rise to the higher energy. And now we calculate for exactly this electronic structure, the Berry curvature, and also the conductivity. And this is now this band structure, and I concentrate, or I just consider only the lower block, since the upper block gives rise to the same result, but with a negative sign, since only the spin is the spin is reversed with respect to the magnetic moment. Now, what is the result for the conductivity? We see the following. Each band, if we start here, gives rise to a jump of E² over h in of E square over H in the conductivity. And then the second band comes, and there is some deviation from it, but there is again a nice plateau. But the higher the dispersion in the system, the plateaus are not anymore so nicely seen, but they are still there. We still have regions, for example, also for this band, with nice plateaus. And also, if we come from the opposite, from the lower part of from the low energy bands, we see plateaus, but they are 2e square over H. Now we wanted to understand this result that we calculated. So, and exactly. Now we try to compare the topological Hall effect that we calculated with the quantum Hall effect. And for this, we first consider the skyrmion number. We calculate the skyrmion number of our skyrmion, and this is related to the emergent field, which is nothing but the Berry curvature in real space. But this emergent field is, of course, an inhomogeneous field in my Brion zone. But to do an analytical calculation, we homogenized this inhomogeneous field, which is seen here, but under the condition that the skyrmion number is conserved. And then we calculated for this homogenized field the following problem. We took now free electrons in a homogeneous magnetic field in a triangular lattice, the same lattice as our skyrmion lattice. And the homogenized field enters now our Hamiltonian by this vector potential. That's what you know from quantum mechanics lectures, that the field enters the Hamiltonian and interacts with the charge of the electrons by the vector potential. And this is the result. Without the vector potential, we would observe free electrons in this hexagonal lattice. And this is this free electron dispersion relation that you see. This is this parabolic shape dispersion relation. And as soon as we switch on the magnetic field and the vector potential becomes non-zero, we have Landau quantization, and all the states condensate into Landau levels. So, and we have, as a function of energy, we have either one Landau levels or we have two, which are whole states or electronic orbits here in this region. Now, let me come to the calculation of the conductivity. The conductivity calculated from this, again, by the Berry curvature of the system, gives rise to a very nice step-like function. And you see the steps are E square over H, always. And only in this region, the steps are 2E square over H. Now we calculated the Chern number. And then you see that the steps that we observe correspond to the Chern numbers in the system. So first step, Chern number -1. Then second Landau level comes in and Chern number accumulates to -2. And these are the steps. Here, in this case, for the lower energy bands, the Chern number is -2. And this is related to the fact that we have 2 orbits per unit cell. So now let's compare the band structure that we calculated before for the skyrmion, for the electron in the skyrmion lattice, and now for the electron in the homogeneous magnetic field with Landau quantization. And you see there is a similarity between the band structures. You have a correspondence between the individual bands, but of course, in the case of the skyrmion, we have really dispersion in our bands, and in this model Hamiltonian, we have no dispersion. We have flat Landau levels. But otherwise, they are very similar. And in particular, if we now consider also, again, the conductivity, we see also the correspondence of the plateaus here and also for the low energy bands. So we have described this conductivity with two different schemes of calculation. Either you observe the motion of electrons interacting with their spin, with an underlying spin texture. This is the left result, and the right result is electrons moving in the emergent field of the skyrmion, and it's now an interaction with the charge of the electrons. Now, I want to show you the surface band structure. The surface band structure is exactly calculated from the real band structure, but you project the solution that you have in the two-dimensional Brownian zone for our system to one edge of the Brownian zone. And then in this surface band structure, you see the bulk bands. If you don't have dispersion, the bulk bands are still lines for the Landau levels. But if you have dispersion and you shrink the bulk bands you project the bulk bands to one edge, you get a real band. You get broad bands here. This is the blue region. But the advantage of the surface band structure is that you see the surface states. And you remember that I told you that there is this one step, E square over H, related to the Chern number. Chern number was -1. There is one edge state, and you see it here in this first plateau. If you come to the second plateau, second gap, you have two edge states in, and you can go further and further, and the number of edge states is increasing until you reach this Van Hove singularity, and it switches from hole to electron states. Okay, and there is also there is really a correspondence between the number of edge states for the motion of the electrons in the skyrmion lattice with this motion of the electrons in the emergent field. The only difference is that we approximated the field by a homogeneous field. For this reason, we don't have dispersion in the right case. Now, I would like to come back to my cartoon about the different Hall effects, and I would like to add the topological Hall effect to this cartoon. And you see that the topological Hall effect is nothing but a quantum Hall effect, as I have shown you, or it's also nothing but an anomalous Hall effect. The only difference is the chiral spin texture. So you see that the underlying spin texture is non-collinear, the skyrmion lattice, but also then the electron moves, the edge channel, the electron spin of the edge channel is also non-collinear and is moving in this way over the skyrmion lattice. So you can understand the topological Hall effect as a quantum Hall or quantum anomalous Hall. They are equivalent in this sense. So now let me come, this is a short part. I just skip my summary. I did it, I mentioned everything, but I wanted to show you the anomalous Hall effect in coplanar antiferromagnets. This is one short chapter that I would like to add. And this work was done together with Oliver Busch and again with Børge Göbel. And coplanar antiferromagnets became very popular over the last years. And you have this structure of the system. We have either hexagonal or cubic antiferromagnets with each plane can be described as a Kagome lattice with a coplanar spin texture. So, and there are different chiral antiferromagnets. There are the one with positive vector spin chirality, which is manganese 3, iridium, rhodium, platinum, or with this negative vector spin chirality. And this is manganese 3, gallium, germanium, and tin. So these are the cubic systems, and these are the hexagonal systems. Further on, I would like to consider the systems with positive vector spin chirality, and so there is many work published on this. I would like to mention that Alan McDonald's group, they published long ago a paper on such a system and predicted that there might be a large anomalous Hall effect in these systems. And coming back to the simple cartoon, usually we understand the anomalous Hall effect being proportional to the magnetization of the system. But now we have a system, it's an antiferromagnet, the magnetization is 0, and there is no simple explanation of the anomalous Hall effect. Now, I take the model Hamiltonian that was also used by Alan McDonald's group. We have, again, free electrons. The Hamiltonian is very similar to the Hamiltonian that I used before, free electrons moving in a spin texture. This is the coplanar spin texture. And then we have a new term that I didn't have before. We have spin-orbit interaction. And
sorry, Ingrid, 5 more minutes.
Yeah, I will be ready. Yeah, and so we are now considering this system has certain symmetries. So since it's an antiferromagnet, time reversal symmetry is broken, but there is mirror symmetry so that T times M is a conserved symmetry. So now let me come to the results. I do the same as before. I calculate this anomalous Hall conductivity as I introduced it before. And so you see, if I do not have spin-orbit interaction in my Hamiltonian, I have the band structure looks like this. I have 6 different bands, and the electronic states are fully unpolarized. So there is no set component of a magnetization. And as a result, it's here you see in my figure a black line. So I don't have anomalous Hall effect in such a system, since I have this certain symmetry of time reversal and mirror plane. Now, if I switch on spin-orbit interaction, mirror symmetry is broken. And so you see avoided crossing occurs, and my bands also, my electronic states get polarized. So I have positive and negative expectation value of spin polarization in Z direction. So now, I would like to understand this anomalous Hall effect, and I would like to understand the mechanism behind. So I do the following. Maybe I go back again, since I forgot to mention, if I switch on spin-orbit interaction, of course, I get this large anomalous Hall effect that was predicted by the authors that I mentioned before. And now, what I do, I take this system and artificially I introduce an out-of-plane tilting. So this was the system that I considered before, and without spin-orbit interaction, the anomalous Hall effect was 0, that this would be exactly this point, and it was 0 for different energies. I have shown you the energy dependence before. Let's now concentrate just to one curve. Let's take the black one, for example. It's a certain energy. It's exactly, it should be the Fermi level. And so what happens now if I switch on this tilting, out of plane tilting? You see that with the tilting, I break again inversion symmetry, and I observe finite values of the anomalous Hall effect without spin-orbit interaction. Now, let me switch on spin-orbit interaction. And if you check the results, you see the following. For this radial configuration, it's not anymore zero. I have a really big anomalous Hall effect, but there comes again some angle of out-of-plane tilting where the anomalous Hall effect for all energies becomes zero. We would like to understand this. It looks like the symmetry, although I have spin-orbit interaction, is again restored. So, and this we tried to show. So we take our Hamiltonian with this coplanar spin texture. And what we do now, we do a transformation. We do unitary transformations to understand why this effect is so large and why this effect is zero here. And after the unitary transformation, I observe the following. The Hamiltonian looks very similar. Of course, these are other operators, and my parameters are different. I have an effective hopping, I have effective magnetic moments, and I have effective spin-orbit interaction. In particular, let me concentrate to this term. I have a new spin texture. With the effective moments, I have a virtual spin texture, which is tilted out of plane. And so this gives rise to the understanding of this value. If I concentrate to, for the radial configuration, the original spin texture, I wanted to understand why I observe a large anomalous Hall effect for this configuration. And the answer is, responsible for this anomalous Hall effect is a virtual spin texture that is caused by spin-orbit interaction. And this virtual spin texture has an out-of-plane tilting. And this out-of-plane tilting causes something like a topological Hall effect. And this topological Hall effect is huge, since it's proportional to the opening angle of the three magnetic moments in the virtual spin texture. Now let me come to the next point that I want to understand. I want to understand this point. Why do I restore anomalous Hall effect being zero for all energies? And this can be understood in the following way. The last term, the spin-orbit interaction, has now an effective spin-orbit coupling constant. And after the transformation, this constant has a certain form, but in particular, it can become zero. And it becomes zero exactly for this angle. And this means that in this configuration for this angle, 103 degree, the virtual spin texture is now coplanar. The virtual spin texture is coplanar. We restored the symmetry, the time reversal times mirror symmetry for the virtual spin texture, and as a consequence, we do not observe any anomalous Hall effect in the system. Okay, and I think this is nearly the end of my story that I wanted to show you. So we have been looking for a microscopic origin of the anomalous Hall effect in Kagome antiferromagnets. We have been showing that the spin-orbit interaction causes the virtual spin texture, and that this virtual spin texture creates something like a topological Hall effect. Similar to the skyrmions, we have this out-of-plane tilting, we have this opening angle of the magnetic moments, and we have this contribution. And this is the end of my talk, and I would like to thank you for watching my talk.
Ingrid, thank you very much for this exciting presentation. This is the time for questions. You can ask the questions, you can type them on the questions and answer box, or raise your hand and we will allow you to ask questions live. There is one question by Bobby Gunara. You mentioned about skyrmions. Does it have relation with the skyrm model?
But, sorry, I didn't understand. Does it have relation with what?
Skyrm or skyrm?
Yes,
model?
Of course. A skyrmion is a spin texture. It's a magnetic whirl, and of course, it's a solution of the skyrm model. Yes.
Are there any other questions? Oh, we have one question here from Juan Sierra. Adriana, could you? Thank you. Juan,
Yeah. Okay. Thank you, Ingrid, for the very nice talk. So I have a question regarding so if I understand properly, so for the topological Hall effect, you need a topological index that comes from the skyrmion lattice.
Yeah.
But the spin texture, so it's not, so what I mean is, instead of having a skyrmion texture, we have like a magnetic vortex texture. We will not have this topological Hall effect because we need an associated topological index, right?
Yeah, also you are right in that respect that the quantum version of the topological Hall effect that I described is related to the topological properties of the lattice.
Okay. Okay.
Yeah, it's really related to the topological properties of the lattice. Otherwise, it's not the topological property of the. You would not get the effect for an individual skyrmion.
Okay. Okay. Thank you. Thank you very much.
Mm-hmm.
So, Sergio, you can unlock your microphone.
Thank you, Ingrid, very much for your very nice presentation. Regarding the virtual spin texture that's coming from a spin orbit effect, right?
Mm-hmm.
So do you find like an energy dependence of this effect for the angular dependence?
Yes, of course. There is a certain energy dependence, and you also see it. Maybe I can go back to this slide. You see it actually. You see it in the individual curve. So yes. In the beginning, I did just artificial tilting of my texture, but now I don't do artificial tilting. I do just include the spin orbit interaction, and you see that you have a certain dependence on the angle. So, and you see that at angle 0, there is a large anomalous Hall effect. And what I wanted to say, it's more a topological Hall effect that we observe. And of course, for other angles, you get also this topological Hall effect. And you see that it also disappears if I approach the ferromagnetic configuration. I wouldn't have topological Hall effect in the ferromagnetic configuration. And I have this certain point where it goes to 0, where this the virtual spin texture approaches is a coplanar texture. So you can say what I do with this spin orbit interaction that I introduce in the electron Hamiltonian here, it's kind of a Jaluzinski-Moria interaction. So it's I just, if I would write it for the action not to the electrons but to the spins, it would be kind of a Jaluzinski-Moria interaction.
And now, if I change the Fermi energy in your system, how would you expect this to change?
If I change the Fermi energy, I should go back. You would observe curves like you would observe this curve.
This curve, okay.
And it would be, of course, if this is now for this spin orbit interaction for 0. it's for the radial configuration. It was at 90 degrees. And it would change a little if I go to another spin. It would change if I enhance spin-orbit interaction and or if I enhance the tilting angle. Yeah.
And this is quantized?
No, this is not quantized.
No situation which is quantized.
This is
not even in the region of the gap here.
Yeah, there is, you are right. There is a little this effect here where you have this avoided crossing gap, and it's a global gap here in this. Then you see that it's quantized.
Okay. Yeah.
Then you really have also an edge state, and it's quantized by 2e square over h. Yeah.
Thank you. And I see that there are more questions.
There are many interesting questions among the panel. Maybe, Adriana, could you allow the microphone of Hiroshi Katsumoro? So, Adriana?
Yeah, it's he's allowed to talk. Hiroshi Katsumoro, if you want to ask your question now. Otherwise, Daniel, you can read it.
Yeah. Thank you for. I will just read the question of Hiroshi Katsumoro. Thank you for a nice talk. I have two questions. One, why does the mirror symmetry in coplanar magnetization disappear when SOC is considered?
When spin-orbit interaction is introduced, or exactly, I would answer with the help of this virtual spin texture, since I have now an out-of-plane tilting of my virtual spin texture, which is caused by the spin-orbit interaction, and then you would see that the system has out-of-plane moment, and so it's not anymore inversion symmetric.
So, and there is a second part of the question, I may have missed it, but when there is no spin-orbit coupling in non-coplanar magnetization, is there any anomalous coupling?
So this is exactly this figure. If there is no spin-orbit coupling, and what was the second part? No magnetization?
In non-coplanar magnetization, if there is no spin-orbit coupling in
no spin-orbit coupling means that my band structure looks like this, and you should look at the gray color. It means all the states with respect to spin expectation value in z direction are fully unpolarized. So I always, for anomalous Hall effect, need a polarized current. So the states are fully unpolarized, and anomalous Hall effect is 0. I cannot show it in my figure since it's, wait a moment, I should maybe, if I go, so it's the black line underneath in my conductivity. There is a black line, 0 line, so this doesn't give rise. Without spin-orbit coupling, I have no anomalous Hall effect.
So we have many other questions. Is it possible to imagine a 3D extension of topological Hall states as we have with topological insulators?
Wait a moment, maybe I didn't understand that. You mean for the skyrmions? Or in which respect?
That's a good question. It's from an anonymous attendee, so I'm not sure how to clarify this question.
But I would just say for the skyrmions, there's actually no simple 3-dimensional version of the skyrmions. In 3 dimensions, the skyrmions are tubes, and every layer would have the same spin texture. And what I need for this discussion of the quantum topological Hall effect is the contact of one of these layers with a free electron gas. You can also imagine you have a free electron, have free electrons moving in the skyrmion tubes. It would give you a similar effect.
So we have another question from Subhankar Vedanta. will anomalous Hall effect be observed in non-collinear antiferromagnetic materials?
Anomalous Hall effect in non-collinear. I mean, I would, after my presentation, I would say, of course, I have also a little, I didn't talk about this in detail. You also get a little anomalous Hall effect here with spin-orbit interaction due to the out-of-plane magnetization. But this out-of-plane magnetization is so small that the signal would not correspond to the size of the signal that is calculated from the Berry curvature. So, of course, if the out-of-plane magnetization is zero, as in this case, there is no anomalous Hall effect. If there is a out-of-plane magnetization, in the integral value over the Brion zone, we would have an anomalous Hall effect in the sense as usual, but this does not explain the large signal that we observe for these systems. This is really related to this virtual spin texture, and what I wanted to say is that it's more a topological Hall effect than an anomalous Hall effect.
So we have 3 more questions,
okay.
4 more questions, 5. So maybe, Adriana, could you allow Subankar to, Young also to ask the question? Young, can you ask the question?
I think Ingrid has already answered the question by talking about the insignificant contribution from the magnetization out of plane to the measured Hall effect. I think that's what I was wondering, because if you have a magnetic field applied out of the plane, whether that can tilt the moments a little bit out of the plane, and whether that could, give rise to some Hall effect. But she already answered that that is just so minimal compared to what is measured.
Mm-hmm.
Thank you. So we have a question by Narayan. Narayan, can you ask a question?
Yeah, hello.
Yes.
So my question is, how stable do you think are these edge states in the topological Hall effect? Because in the pictures that you showed earlier in the quantum Hall trio, I see that a spin flip transition in the integer quantum Hall case would not destroy the quantization. Whereas in the quantum spin Hall case, it does destroy the quantization, and we see this whenever there is a spin flip transition. But in case of the edge states in a topological Hall effect, you show that the spin is changing continuously. So
Yes.
how stable are these edge states, and what prevents it from what prevents these edge states from mixing with the bulk?
I mean, you're fully right that, of course, in the quantum Hall regime, the edge states are protected by topology for backscattering, or for scattering into each other. So it's no scattering in these systems. In the consideration for the quantum topological Hall effect, you're right. If I would have more than one edge channel, of course, there might be the opportunity that there is some transition or some spin flip between the states, and that they would change, or that I have a scattering between the states. But actually, this we didn't consider yet. This is an interesting question. We didn't consider it yet. At the moment, we just considered a certain edge channel that, as you have seen from the band structure, survives. And actually, maybe I could go back to one of my slides. With the band structure. This. Here you see the following. So here I think the edge channels are really stable in as soon as they are in the global gap. But what you see, your question interaction also with the bulk states, you see it here. You see it nicely here. that as soon as there is, of course, there is hybridization between the edge channel and the bike states. You see that. And this is also the case that the quantum version of the effect is destroyed. This little dip is not a numerical error. This little missing of transported charge comes from the Hall effect of the bulk states. So there is, you can imagine, there is this edge channel, and then there comes the bulk contribution. And the bulk contribution is not an integer contribution and reduces the edge channel contribution by a certain value. And you can see it everywhere. As soon as you have dispersion, so the plateau is always nice if you have a large global gap. And as soon as you have dispersion, here the plateau is not formed so well. Yeah.
Okay, perfect. Thank you very much.
So the next question is by Diego Rosales. Diego, you can ask your question directly using your microphone. Diego, are you there? Okay, we can continue with an anonymous attendee question. What are systems other than you shown here where you can expect the topological Hall effect?
I mean, by my opinion, every system that has a non-collinear spin texture with an opening angle should give rise to a topological Hall effect, either to the non-quantized version or to the quantized version. So there was this other question before, the contribution of an individual skyrmion to the topological Hall effect would be the non-quantized contribution. And this lattice topological Hall effect that I discussed is of course the quantized version. And I would say every spin texture that has an out-of-plane tilting and forms an opening angle is a source of a topological Hall effect. So in this respect, you could also say, I mean, that this non-Coplanar antiferromagnets, they are a mini skyrmion, if you want so. The virtual spin texture is something like a mini skyrmion, just given by 3 spins. The skyrmion people would not like it, but it's just to illustrate. It's also not mathematical correct what I said. It's not a skyrmion in the mathematical sense, but it's with respect to formation of an opening angle, the system is similar.
So Diego, are you connected?
Yes, thank you.
Okay, your time.
Thank you very much for your talk. Ingrid, my question is related with the spin texture and the first part of your talk. What's the situation if both a spin texture and charge degrees of freedom have dynamics? The question is if you can modify the electron dynamics, can modify the spin textures.
Yeah, this is of course not considered in my calculations, but this is something that we are working on. So how would these effects be modified in case if you do not consider a DC current regime, but if you stimulate your system with a femtosecond laser pulse, for example?
Okay.
So of course, we expect, and from what we know and what we have done until now, we know that there is magnetization dynamics. So the magnetization is changing. First, the electrons are excited, and as a consequence, we have change of magnetization. And then, of course, these effects would be modified strongly. But I don't know the answer yet.
Okay, thank you.
So Ingrid, thank you very much again for this wonderful talk and a nice discussion. I propose that we continue a little bit in the alternative lunch break
Yeah.
So if there is anyone interested in discussing directly with Ingrid, she will be available for a few minutes. If not, I want to thank you everyone for the participation, particularly to you, Ingrid, again. And let's meet again in the afternoon session in the link provided in the email. You all have the Zoom link in the chat. In case you don't have it or you don't see it for any reason, if you register for the conference, you should have received an email with the same link. Thank you very much and see you in the Zoom.
Okay.